Today we're going to look at the NSK Megatorque motor with the NSK Copley proprietary drive. And I found this on the internet about the variation on the PS motors, and able to click and download the data sheet. The data sheet contains information about the motor we're going to use today, the PS3090. 90 Newton meters of peak torque, 30 Newton meters of continuous. 5 revs per second. We can run it like 300 RPM with 240 volts. I'm going to run it with 120, so I'll keep the speeds less than 150 RPM. The inertia of the motor is 0.024 kilogram meters squared. I've got an inertia that's about 10 times that to act as a load, so 0.24 kilogram meters squared. The counts per rev is 2,621,440 with plus or minus 2 arc seconds. I think that's about 500 counts. So that's our goal for tuning. So let's see how to connect the drive and motor, and then we'll run CME2 to load the file. I've got the NSK proprietary resolver type feedback, which is single turn absolute with the 2 million counts per rev. I've got the motor's power wires connected, UVW, white, black, red, and earth. I've got 24 volts, that's the keep alive. That also allows me to connect over the serial port with the SER-CK and the B&B Electronics USB to serial adapter 232USO9M. And I have the safety bypass jumper, which I can use to bypass the stove, but we'll do that in a moment after we run CME2. So connecting CME2 over the serial port, we find our COM port, we select the 115 kilobit baud rate, that's standard, and we're going to load the CCD file. The CCD file contains the encoder correction table, plus the tunings with no load, plus all the motor data. And this gets loaded directly into Flash, just like FOE, file over EtherCAT. And the drive will come up in a safe mode, and we can take a look at the control panel. So it's just resetting now, and we'll be able to talk to the drive in a moment. So it just uploaded the data to CME2, and so we have the stow, which we have to hook up the safety jumper, and the drive is still disabled because there's no EtherCAT master or CAN open for a CAN open drive, but we can enable the drive, and we can start jogging with no load. So we're just going to take a quick peek through on the configuration. We have a brushless rotary motor. We have a resolver NSK incremental absolute. That's the proprietary feedback device. It does not work on standard Copley product. We can emulate encoder out. And we see all the data for the motor, the poles, the inertia of the motor, the speed limits are set, the feedback device, and we can, if we have a brake, we can set some, reasonable time to stop the motor to a slow speed before engaging the brake and wait for the brake engagement delay time. No need to calculate values. We've got values that have been tuned and stored into the CCD file. We can check the current loop bandwidth, which should be about a kilohertz if we have it tuned up close to the necessary bandwidth. More or less is fine. We don't need to rotate the current vector very fast. You can see the peak and continuous current peak time 10 seconds at 4.9 amps. So we can hold out at the peak current for a long period of time. Future software should have more features for that, but right now I'm using CME 2 version 7.1 beta 30 engineering release 7, so we'll wait for hardware features and firmware features and CME 2 features to come, but just getting started here. We've got some tuning values. I like to keep the integral low so that we don't over-integrate when we attach the load. The proportional gain does not cause buzzing here, but when we attach the load we can increase that. There's also a reasonable tracking window for speed, so we're not bothered constantly by velocity tracking error. It's just a warning, sorry, velocity tracking warning. The P-loop and feed-forward terms are default. We can set the wrap to the number of counts per rev, so it goes back to 0 when it hits that number. I lowered the fault to 1/8 of a rev and a warning to 1/4 rev. I left the tracking window at 500 counts. We need sufficient gain to ever settle. You can open that up a little bit longer if you want. And I should also note that the filters are configured with one single pole filter at 100 Hertz. You know, we can move this pole out if we want to try to crank the gains up, but it gets a little buzzy and noisy, so most of my direct drives use about 100 Hertz. So we can take a look at the velocity tuning here. I don't like to bang it back and forth so fast, and I like to lower my velocity parameters. 6 for XL and decel seem pretty good. And on the settings tab we can move the time out a little bit so we can try to capture some of this plus or minus 33 RPM motion. So we can see the gains have been adjusted for the no load condition. And we can also take a look at the profile auto setup checkbox. This is 1/10 of a rev, so we'll do 1 full rev. And I like to monitor the in motion bit to see how we settle into the position. So this will be a trajectory move, 120 RPM, 5 for XL, 5 for decel. There's some jerk options that I've set for S-curve. We'll look at that after we attach the load. And we can see we've moved and settled to within 500 counts in a reasonable period of time. We can add some more integration here if we want to settle closer to 0. But we're within 200 counts already. It's 2 million counts per rev. So I'm going to attach the load now and we'll take a look at this again. As you can see, I've attached 10 pounds at either end of about a foot, and I can make the move with the larger inertia. My inertia is greater than 10 to 1 because I see clipping of my peak current at about 5 amps, so that's more than 10 times the no load current required. There's a little bounce, takes a little longer to settle. This is the bounce of the electromechanical time constant based on the inertia and the gain settings. I'm going to give it substantially more proportional and integral gain, proportional velocity loop and proportional position loop gain. I can lower the integral a bit. Over integrating is not necessary. But I still get a little clipping because of the electromechanical bounce. So I'm going to try a little S-curve profiling here. This should give us a little smoother for XL. Going to round off the corners a little bit, and we get a little better. Still have a little over integration there, so I'm going to turn the integral down. Oh yeah, that is too big. 500. Maybe even 250. We don't want to over integrate. Yeah, following her settles to 0, plus or minus 500 counts at the end of the trajectory. So even though it looks like it may take a little bit longer to do S-curve, its ability to settle quickly actually reduces the time it takes for in motion. Okay, I want to check that I have the encoder correction table turned on. I see a little buzziness in the feedback there. That looks actually pretty good. So we'll go to Tools, ASCII Command Line, Get from RAM 0x13E. I have a value of 3. That says that it's been turned on if I set this to 0, then I should see the correction table turned off. It sounds a lot buzzier, and we should have a larger following error. There we go. So with the correction table turned back on, we set the bit. OK. So the correction table turned back on. Much more efficient. I had some resonance here, so I'm going to turn the VP down a little bit. I may have been a bit aggressive with that. My integral still looks pretty good, and I'm going to say good tuning. We can save a CCD file with these parameters. Say inertia times 10. So CCD file, all tuned up, ready for the large inertia, and done for the day. Thank you very much.